experiment is conducted to investigate the photoelectric effect with an unknown metal plate. When the wavelength of the incident light is less than or equal to 475 nanometers, the plate starts emitting photoelectrons. So here we have our light coming in. It's hitting this unknown material plate, metal plate, and this is held at a negative potential. Here's a little battery here. So the electrons leave there and go over to the other side. This is the collector, which is at a positive potential. So what is the threshold frequency of the metal? What is the work function of the metal? We then change the wavelength of the light to 425 nanometers. What is the kinetic energy of the photoelectrons? What voltage does the battery need to apply to stop the electrons from moving through the circuit? What is the threshold frequency of the metal? Well, the threshold frequency is the minimum frequency needed to eject electrons. It can be found by solving for the frequency of the maximum wavelength, right? Because wavelength and frequency are inverse. So we use the speed of light here. C is equal to lambda f. Solve for frequency. Input in the speed of light, right? Because we're talking about the photons, which move at the speed of light. Divide it by the wavelength. And remember, to convert 475 nanometers to meters, you add 10 to the minus 9th meters there. And we get a frequency of 6.32 times 10 to the 14th hertz. What is the work function of the metal? Well, let's use our photoelectric effect equation, where here's Planck's constant times the frequency is equal to the Ke of the emitted photoelectrons plus the work function, which is the amount of energy you need to free the electrons from their atoms. So when using the threshold frequency, set the kinetic energy to 0. You want these photoelectrons to just barely leave and not have any motion really. All frequencies below the threshold frequency result in kinetic energy equals to 0. All frequencies above that, you'll get greater and greater values for kinetic energy. So HF is equal to the work function. The work function is equal to HF. What is the work function of the metal? Well, you can work, get it, little pun there, in either joules or electron volts, depending on which value of Planck's constant you choose. Here you choose the joule second one, and you get the work function is 4.20 times 10 to the minus 19th joules. On the right side, we use the EV second one. Both are equivalent, just slightly different units, and we get the work function is 2.62 electron volts. So now that we have a wavelength of incident light at 425 nanometers, what is the kinetic energy of these photoelectrons? We anticipate it won't be 0 anymore. So we have the wavelength decreasing, so the frequency increases. So again, no longer at the threshold frequency, so the electrons will have some kinetic energy. The work function stays the same. That's a property of the metal plate that will not change depending on the light frequency. So we're going to use, once again, speed of light is hf, and f is equal to c over lambda over here. Okay, so this is the equation we're going to be using. Again, we can solve in joules or electron volts, but make sure your units for Planck's constant and the work function match and convert the wavelengths to meters. So first we'll do joules. All right, here's Planck's constant in joule seconds. Here's the speed of light. And the work function here that we found in joules is 4.20 times 10 to the minus 19th joules. And here's the wavelength. 425 nanometers is 425 times 10 to the minus 9 meters. Multiply through, and we get the kinetic energy is 4.80 times 10 to the minus 20 joules. Now find the kinetic energy in electron volts. So what's different? Planck's constant in EV seconds, and the work function in EV, same type of math, and we get the kinetic energy is 0.30 electron volts. Find the equation for the stopping voltage. Well, the equation for the stopping voltage is right here. Kinetic energy is equal to the charge on the electron times the stopping voltage V0. So V0 is kinetic energy over the charge on an electron. Working in joules, here's our energy, 4.8 times 10 to the minus 20 the joules. Charge on an electron is 1.6 times 10 to the minus 19th coulombs. We get a stopping voltage of 0.3 volts. Now, if we work in electron volts, same equation here, but the kinetic energy is 0.3 electron volts divided by E, the charge on the electron. Those cancel, and we're left with 0.3 volts. And of course you get the same answer regardless of the units we're working in.